Okay, welcome back. Hopefully you got a coffee or did whatever you had to do to relax a little bit. And hopefully the first part sufficiently inspired you to learn more about how we do our process calculations. I wanted to quickly apologize. I didn't realize that my video was not on. Apparently you have to see yourself as a bubble in Zoom in order for you guys to see me, and it's a little weird to see myself, but here we go. So just to make sure you can see me, I'll have to see myself. Okay, so let's start with our process calculations, and we're going to take a look at reaction rates, equilibrium, the history of how people have applied our process calculations, networks, reaction networks, astrophysical trajectories, our process dynamics, and so on. So again, these are the slide numbers corresponding to this particular section. This is going to be a bit of a heavier section compared to what we just saw for the background with sites and observation. Okay, so first, this is really going to be a reference slide for you. If at some point you see something within this talk, some variable, and you're thinking, Nicole, where did that come from? Please just go back to this slide. So this is some definitions and an introduction to astrophysical rates for a particular reaction. So the first one that you're going to see quite often within nuclear astrophysics and even within this particular section is the Q value. So the Q value can be written as the sum of the masses of your reactants minus the sum of the of the masses of your products. So if you have a positive Q value, you have energy released. And if you have a negative Q value, your reaction needs energy in order to go. It needs to absorb some energy in order to proceed. So the larger and more positive of a Q value you have, the more likely you're going to have a reaction move forward quickly. Okay. Another thing that particularly for the R process shows up as an important quantity is the 1 neutron separation energy, which is defined here for a particular species. So you have to take into account the mass of its neighbor plus the mass of the neutron minus its own mass. And of course, this is missing a factor of C squared here. C is 1. Basically, we're going to have units of MeV for these. Next, we're going to have number density. Now, this is just the number density of one of your initial reactants, B, and that's going to be equal to your density times Avogadro's number times something called mass fraction over your mass number. So we described mass number in the first part of this talk. It's going to be your number of protons plus your number of neutrons. And mass fraction is essentially going to tell you how much of each species you have in such a way that they all sum to 1. So it's like a relative number relative to all of your other constituents within the network. Abundance is defined as mass fraction over mass number. Okay, so whenever you hear me say abundance, or maybe whenever you see on plots mass fraction, now you have this nice easy reference as to what those mean. We already defined YE up front in terms of neutrons and protons, but another definition of YE that sometimes comes into play within the equations and rate calculations relevant for the R process is that YE is this sum of your proton number times the abundance of that species. And note that this assumes charge neutrality. Okay. All right. Next, we have the interaction rate, R. It's going to be your number density of your 2 reactants times this factor here is just going to be something that corrects for overcounting. If these 2 are the same, then this becomes 1, and you divide by 2 in order not to double count, okay? In order not to double count your species. This right here is your thermally averaged cross-section, which typically, because these are nucleons, you're going to average over a Maxwell-Boltzmann distribution. So that's all written out here more explicitly, okay? Now this, when put all together, is called your interaction rate or just simply reaction rate, and it has units of per second per centimeter cubed. Now this is when you take out your target nucleus, and sometimes this is referred to as stellar reaction rate. So you can see it's pretty much the same thing, except you're going to take out your target nucleus, okay? So hopefully you don't get too confused with these. They differ by a factor of a number density. All right. But again, if you see something in future slides where you're wondering, okay, what is that quantity? Please come back to this slide. Okay, so before we can talk about networks and reaction rates, we need to talk about equilibrium a little bit, because equilibrium assumptions are something that go in to astrophysics calculations. If you have very high temperatures, very high densities, this is something that can be achieved within astrophysical environments. So if your environment is hot enough to overcome Coulomb barriers and has higher energy photons, nuclear statistical equilibrium assumes that photodissociations are going to be in chemical equilibrium with your captures of neutrons and protons, as can be seen from this equation. So this is going to give you this equation right here, which essentially balances chemical potentials. So chemical potentials for nucleons and nuclei are going to be determined from Maxwell-Boltzmann distributions. So here's an explicit formula for your chemical potential. And then it's through these equations that are balancing your chemical potentials, as well as the fact that mass fraction has to sum to 1, and that we have YE equal to this sum ZYI that I mentioned before in our definition slide, that you're able to solve for abundances. This gives you a system of equations where you can solve for the abundances once you know your density, temperature, and YE. So this right here, this plot, is just an example of calculations for the mass fraction from NSE for a particular density and a particular YE as a function of temperature. So this is for a YE of 0.5. So you're more proton rich than we are in the R process, but nevertheless, it demonstrates the things that are also relevant for our process calculations. So I really like this plot. You can see explicitly that for high temperatures, you're favoring free protons, neutrons, and alphas. Then at intermediate temperatures, you're favoring alphas. And then when you go to lower temperatures, you're going to be favoring things that are particularly well bound. So things like iron and nickel. Okay. So this is something that during certain conditions, you can get the abundances from these NSE considerations, and that will come up a bit later again. But this is just a very nice introduction to equilibrium and its importance within astrophysics. Okay, so let's recall just a few of those definitions from the beginning: Q value, reaction rate, stellar reaction rate, and number density. And I'm just going to have them up here for reference. Now, what if we wanted to calculate the reverse rate? So C plus D goes to B plus X. Well, this tends to be done by something called detailed balance, which again is an equilibrium condition. This is often also called the Saha equation, okay? All right, so if you have B not equal to X and C not equal to D, and everybody is nuclei, your equilibrium condition is that the forward rate and the reverse rate are equal. This gives you this relation here, a ratio of number densities to your average sigma v, your thermally average cross section. And then there's this particular relation, which if you want to see the derivation, I encourage you to look at this paper. They have references to all of the original works which derive all of these considerations, but there's an explicit connection between the cross sections of these two interactions. So then putting this all together, you can obtain this, where essentially if you have the reaction rate in one direction, you can get the reaction rate in the other direction, or you can get the ratio of your number densities, etc. So this gives you relations between the number densities of constituents or rates if you need. So this type of equation is called a Saha equation. So if instead you have a photon, you're still going to equate those rates, say that C is a photon, you get this type of relation here, which ultimately is going to give you the rate for photodissociation. So this is important for our process considerations because this tends to be how we get photodissociation rates. So neutron capture is a very important process within the R process. Of course, it's rapid neutron capture. So you have a neutron being reacting, and then it's going to have a product and spit out a photon. So the reverse of that, photodissociation, is something that is very important to be able to calculate within your R process. And this is how we tend to get photodissociation rates, by doing this type of detailed balance. So Saha equations give you reverse rates, and it's a really a nice way to not have to calculate everything from scratch. And we do make use of it within astrophysical reaction networks. Okay, so independent of networks, there was a classical approach to our process calculations that make use of equilibrium considerations. So again, we're seeing how important it is to understand equilibrium and be able to apply that within astrophysics. So the classical approach was to just assume, okay, you have really a lot of neutrons for an R process around. So you've reached an n gamma gamma n equilibrium, and then you're going to couple this with something called steady beta flow or steady flow. Okay. So when you do assume an n gamma gamma n equilibrium, you're just going to apply your Saha equation. And I've written this out more explicitly. So this is going to give you your abundance of neighboring isotopes. Remember, you can relate your number densities back to abundances, and then you know what your relationship, your ratio of your number densities are from a Saha equation, where I've put explicitly in some of these values for an n gamma gamma n reaction. Okay, so I encourage you to work this out. Go from the Saha equation that I just had in the last slide and work through to obtain this equation. So essentially, this assumption, this equilibrium assumption, is going to set the relative abundances along an isotopic chain. So it tells you for a given Z, what is your abundance of at mass number A compared to A+1, compared to A-1, etc. So that's what determines a chain's abundances. Now, if you're going to evolve these abundances, this is done within these classical calculations by the flow of beta decay. So what is done is to just have more of a sum of things. So you're going to have the number density at a given Z. Rather than the number density of an individual species, you're going to consider the number density of a given Z. And you're going to say that that evolves in time according to this relation, where this is going to be a beta decay rate that is sort of like an average rate. So it's going to sum over all of your rates and multiply by the number density of your constituents. Now, steady flow equilibrium or beta flow equilibrium is when you assume that these are constant and you assume that dNz dt is 0, okay? So you could either have this piece, if you assume that it's not constant, tell you how the chain moves. So this is going to set your relative abundances, and then this is going to tell you how it moves from one proton number to the next. Or if you assume steady flow, this gives you the relative abundances along an isotopic chain, and this gives you the relative abundances along a given neutron number, okay? So this is also sometimes called the waiting point approximation, because of this average means that each nucleus, that they will have to wait basically until the longest beta decay timescale. So your longest beta decay timescale is going to come in and have to make things wait. Okay. Okay, so another important thing you're going to see in the literature, in the R process literature, is the R process path. And this is kind of a term that originates in these classical calculations, because as you can see here, this is 4 different what we call R process paths, or the location of the maximum abundance for all isotopic chains. So essentially what N is most populated at a given Z, okay? Now this is 4 different ones in a study where they looked using classical calculations at what are the number density of neutron and temperature relations that are able to best fit the solar abundance peaks. So there's 4 of them in here, and they correspond to this line, and this actinide line, okay? So you can see here some of these neutron density and temperature combinations that they considered. Also, just quickly, here's some terminology that I would like to let you know about. If you ever hear T9, 10 T9s is about 1 MeV. And the T9 is coming from the fact that we're in gigakelvins. Gigakelvin is a range of relevance for nucleosynthesis. Okay, so this idea of this path is again coming from the fact that you're setting your abundances by equilibrium and by steady beta flow. So you can just say where within the nuclear chart your abundances are sitting, okay? Now, something else that you should notice from this is they have this line here, and then it says freeze out. So it's beyond this line is when you have freeze out, which is defined as when equilibrium fails. So you can freeze out from NSE, so you've frozen out from that particular equilibrium, or you can freeze out of N gamma gamma N equilibrium, which this is what this is referring to here. So something like this can be prompted from when you have a neutron to seed ratio going to 1, you're losing neutrons, or it can just be prompted by lower temperatures, as you can see here, because you can still have high neutron densities, but be in freeze out. Okay. Okay, so this is just showing now an example of what happens when you remove that steady beta flow condition and actually do a time evolution depending on that equation that I showed earlier. So this is an earlier time going to a little bit later, and then an intermediate time, and then towards the end when you filled in all of your main R process. Additionally, what they've done is to demonstrate that at this intermediate time here, your steady flow is a pretty decent assumption, because you have, this is your quantity here, your abundance times your rate. At a couple of neutron numbers, this is pretty much flat, okay? So there are some conditions where this is a pretty good approximation, but once you reach freeze out, once you're out of N gamma gamma N equilibrium, you really need to take into account the competition between all of the other rates involved. So it's no longer a good approximation. So you really need networks for late times in the R process, or if you just want to do things in a little bit more of a careful way and not assume that you can produce an N gamma gamma in equilibrium in all of your conditions. So a short intro to networks. Again, I'm going to have my equations up here just for reference, just something to sort of keep us grounded in things that we've seen before. So say that you have a two-body reaction, B plus X goes to C. Then your change in your abundance of B is going to be the number density of B multiplied by the rate at which B and X interact, and it's going to be negative because you're losing B. So this can be written out if you take your reaction rate here and you put it in. That can be written out more explicitly in this way. Now C is gained by this same value, but now we have it being positive because we're gaining C in this reaction. Okay, now say that you have an additional thing to consider when it comes to the abundance of B. Say that you have D decaying into B plus C. Then you have the same piece from before, from when B was reacting with X, but now you have that B can appear when D decays. So you have to add a term which is dependent on the number density of D times the rate at which D occurs, okay? And likewise, your D now is just going to be determined by this decay if this is the only thing in the network that D can do is just decay. But I'm essentially using B to highlight that an individual species can undergo many different things. It can capture, it can decay, it could have things decay into it. So there are a lot of terms that then have to be considered. So network equations can then generally be written as your abundance as a function of time, y dot, that's just dy dt, is the sum of the one-body decays plus the sum of the two-body reactions plus the sum of three-body reactions. And these coefficients are going to be positive when I is created and negative when I is consumed. And you're also going to have terms like this 1 plus delta, which are going to correct for overcounting. So this is that type of term, okay? It's just overcounting. Okay, so these are going to give you a system of coupled differential equations. And as we know, when we have coupled differential equations, we can put them into a matrix form. So equations use matrix, or networks use matrix solvers. So in a more schematic way, what this really means for the R process in terms of reactions is you're going to have Y change by adding all of the two-body reactions that give you I, minus the two-body reactions that take you out of I, plus the three-body reactions into I, minus the three-body reactions out of Y. So two-body reactions, things like neutron capture, photodissociation, which we've discussed pretty extensively here. Three-body reactions of relevance to the R process, alpha alpha n, n2n. This is where you capture a neutron, but then you can emit two neutrons, okay? Then you have to take into account the decays into this state or the decays out of this state. So things like beta decay, beta delayed neutron emission, where you're going to beta decay and then neutron emit over. Things like alpha decay are important as well. Additionally, fission is something that can come into your calculations if you have neutron-rich enough conditions to get all the way up to these fissioning regions. So either you have a species that's going to fission and then it has to be negative because you're fissioning out of that state, or you have something fissioning and producing a product into this state, okay? There are also three channels of fission that we have to consider within the R process: neutron-induced, beta-delayed, and spontaneous. We'll talk more about fission in the next part of this talk. But for now, this is just a schematic to understand all of these different reactions that go in. I also wanted to make a note here about the different types of reaction networks that are used for the R process in the current literature. So that includes PRISM, Skynet, NukeNet Tools, XNet, and WinNet. And then here are two different papers, which I highly recommend if you want to read more about reaction networks, solving reaction network equations. They go through things in a very instructive manner. Okay, so something that's really useful to be able to do is evaluate something called flows. So say that you want to understand what's going on within your nucleosynthesis calculation. You have all sorts of reactions that could be occurring for an individual species and all sorts of decays at a given point in time. So at a given point in time, Zn could capture a neutron, or it could photodissociate, or it could beta decay, or it could beta delayed neutron emit, or it could alpha decay, or it could fission. And all of these things are in play at once and are in competition with each other. Okay, so you have to put them all within your network, including the probability that one of them is occurring at a given time. All right. So there's a lot going on. So you may want to look at the flow of an individual species, which is your rate times your abundance, to understand what it's dominantly doing with respect to one of these channels. Another thing is if you want to study what a given reaction channel is doing across the nuclear chart, you can take a look at flows of given reactions. So for example, here is a beta delayed fission flow at a given point in time. This is at 1 second, where higher color red is more flow. Okay, so it's something that's more abundant and interacting more strongly. Okay. Here is a neutron-induced fission flow as well at that same point in time. So you can look at these things and analyze, okay, who's dominantly who is dominantly undergoing neutron-induced fission within my calculation? How do beta delayed and neutron-induced compare at this point in time, etc. Another thing that you can do is integrate flows over time, which I've shown here for beta delayed and neutron-induced fission. So you can integrate them over all of time to be able to look at, okay, which species have undergone a lot of neutron-induced fission in my calculations. And in fact, for these fission calculations, it's really interesting. It tends to be up at this predicted shell closure of n = 184. Okay. But this is just a demonstration to show you how useful flows are to analyze what's going on within your network at a given point in time or over all of time. So I also mentioned that another thing that flows could do is to look at an individual species and be able to know what it's doing primarily at an instance in time. Is it mostly capturing? Is it mostly beta decaying at a given point in time? So let's take a look at a movie which analyzes exactly that. So what you're going to see is all of these nuclei are going to be color-coded by the dominant flow at a given point in time. So anything color-coded N gamma is going to be dominantly neutron capturing. Anything color-coded blue is going to be dominantly beta decaying. Red for neutron-induced fission, purple for beta delayed fission, yellow for alpha decay, and green for spontaneous fission. So you're going to watch this evolve in the nuclear chart as a function of proton number and neutron number, and also the temperature and density are going to be listed here. Additionally, up top, we're going to plot our abundances and compare them with the solar abundances. This is something we just love to do in our nucleosynthesis calculations, is see what kind of features are coming out of our abundances, how well do they match solar features. Okay. All right, so let's play this movie and watch it happen. So we're going to start out in nuclear statistical equilibrium at a pretty high temperature. That's how we get our seed distribution. Then we're going to fall out of nuclear statistical equilibrium. We're going to neutron capture over. Then you can see that we have to beta decay. You can see the beta decay waiting points before you can capture. Now we're decaying back to stability, and you can see that fission has come in, is terminating the R process and depositing material back into this region. Now on longer time scales, we're going to have Alpha decay and spontaneous fission come in and shape these actinides at very late times, but otherwise the entire main pattern was set on the order of seconds. And I want to go back to emphasize that again because it happens really very quickly. So you can see here, I'm going to go all the way back. We have moved all of our stuff into the actinides. It's a very neutron-rich condition. Now we're fissioning and filling back in this region of the lanthanides and near the second peak. And right about here, we're pretty much done with our abundances, and that was on the order of seconds, okay? All right, so hopefully this showed how useful it is to be able to look at flows and what things are dominantly doing, and that you have a lot of different reactions going on at once. To consider within the R process, and also how far from stability our calculations go with a lot of, this is a merger condition, something very, very neutron rich, something like a tidal tail that we talked about before. So we went almost all the way to the edge here, which is called the drip line. It's where you can no longer capture a neutron, it'll just get spit right off of the nucleus. Okay. All right. So an advantage of networks and using networks instead of these classical approaches where you just set a neutron density and a neutron temperature is that you can make use of simulation and simulation tracers because networks explicitly take into account the time evolution of the temperature and density of a particular mass element in an astrophysical environment. What we call this is a trajectory. Okay, so what you're going to see here on the left is going to be a simulation of a neutron star merger. And on the right, an overhead view of our trajectories that we're able to get. They're going to have tracer particles within the simulation, which log the temperature and density of this particular mass element. And then we use them later in the R process. But let's first look at how this evolves. Okay, so we have the neutron stars merging. Here we go. All right, here we go. Material is now flung off with this tidal tail here. That's this little blue guy here, and the rest of this is just spat out in the other direction, which you can see here. Now you're also going to see that the simulation ends on the order of milliseconds. So these are very, very expensive, these hydrodynamic simulations. They tend to only run them to tens of milliseconds. So to do our process calculations, as you just saw, we need to go on the order of seconds or longer if you want to look at the longer time evolution of abundances. So we have to extrapolate those trajectories. We have to take what we get from simulation and extrapolate beyond the hydrodynamic simulation information that we're given. So typically this is done assuming free expansion, homologous or adiabatic expansion, where you have your density at a given point in time be dependent on the initial density, which you tend to just take as the last density value that you got. And then you have your temperature, your time have this type of relation going like t cubed, 1 over t cubed. So you can see this explicitly here. This is a simulation tracer in green. This is the extrapolated version of the density in black. Now, another thing that has to be considered when you're looking at your temperature evolution, so this is how you treat your density extrapolation. But what about your temperature? What do you do for temperature? Well, you have to consider that there's going to be reheating of your system from the nuclear reactions that occur. So we talked about how you have high positive Q values mean things happen quickly. Well, Q is heat, right? So this is going to go into your environment, heat your environment. So there's a feedback. This is called self-heating or reheating, since the changes in the composition from nuclear reactions are going to heat the system and in turn affect your nucleosynthesis. So the way that this is treated then is that you're going to take this density evolution that you have determined from free expansion. You're going to take the initial entropy of your system, and then you're going to calculate the change in entropy by taking a particular nuclear equation of state. You're going to assume an equation of state, and your equation of state is what couples your density back to your temperature, okay? And it's also going to be dependent upon your composition here, so you can see that more explicitly here. Here's your simulation tracer. This is what you would get if you just assumed, okay, I'm just gonna take this trend and extrapolate. And this orange is what you get when you do this more correctly and you account for reheating or self-heating. It's a really important thing to consider within conditions that fission, within conditions that are very, very neutron rich and go all the way up to those actinides. That's where you see these things like these big reheating bumps. Some conditions where you don't have, you're not going as far, you see much smaller reheating bumps. So it's not something that that dramatically affects the outcome of your calculation. But here it's a really important piece to take into account. Okay, so introduction to timescales and our process dynamics. So this is an example, before I get into it a lot, of here is a temperature calculation here. Let's take a look at this blue outflow, where you include reheating, but you only see like a very little bump coming out of it from this particular type of condition. And that's because this is a more moderately neutron-rich condition. It has a YE of 0.2, so it's not something that really gets into the fissioning regions. But what I want to look at is the fact that these two are very, very distinct types of astrophysical outflows, we call them. This one is, in slang terms, a hot outflow, and this blue one is, in slang terms, a cold outflow. So what does that mean? So hot dynamics are when you have an extended N gamma gamma N equilibrium. And cold dynamics are when you have photodissociation fall out of your calculation early. It can't compete very early. This down here is called the time scale. It's going to tell you about how all of your reactions are competing at a given point in time. So you can look at flows, but timescales are also something that's very interesting. It's all summed up. So it goes like 1 over rate. Then we weigh it by the abundance and we take a look. So first we can see, let's take a look at the hot case. The solid line is N gamma, it's neutron capture. The dotted line is photodissociation. And you can see that you have this period of long N gamma gamma N equilibrium. These two are competing, they're equal, they're together for a long period of time. Also note that since time scale goes like 1 over rate, the lower this is, the more influential your channel that you're looking at is, your reaction channel is. So you can see that this equilibrium persists for a pretty long time, and then your photodissociation falls out and just goes out of the calculation, doesn't influence things very much. Still some local effects persist, but globally it's falling out. You're falling out of equilibrium. And beta decay comes in and starts to be the dominant shaping mechanism within your calculation. For a cold R process, you can see that first of all, this is happening much earlier, that you have this falling out of equilibrium happening here. And then for a period of time, there's really a new competition that reigns within your shaping of abundances. And that's going to be a competition between neutron capture and beta decay, rather than a competition between photodissociation and neutron capture. So these are two very distinct types of our process. And in fact, cold dynamics, you can see that you have freeze out pretty early here, but you're still shaping your abundances after freeze out, okay? So let's take a look at this a little bit more technically and explicitly. So I'm going to go through this a little bit slow because there's a lot going on these plots. But let's take a look at a hot R process that undergoes an extended N gamma gamma N equilibrium. Over here, we're going to look at the dominant flow. We've already looked at a movie of dominant flow. But this time we're going to take a look at photo dissociation explicitly as well. So we have pink is going to be if something is dominantly neutron capturing. Yellow is if something is dominantly photo dissociating. Blue is if something is dominantly beta decaying. Red is going to be our most abundant nucleus at a given Z. So it's our R process path, remember from before. That's going to give you your R process path at a given point in time. And then the boxed values are going to be what you would predict your R process path to be given n gamma gamma n equilibrium. So this is going to show us explicitly how well n gamma gamma n equilibrium is holding and for how long it's holding for this type of case. The purple, by the way, is just where we have beta decay information. It's not important for this particular exercise and trying to understand what's happening here. And on the left, we're going to watch the evolution of the abundances. So let's go ahead and play it. You can see that that n gamma gamma n equilibrium is holding for a while. Okay, our abundances are still being shaped. All of a sudden, we're breaking out of equilibrium here, beta decay, and you can see all of this shaping that still happened at later times after we broke out of equilibrium. So this is why networks are especially important, even in these cases. You still have shaping of abundances at these late times after you've broken out of equilibrium. But that's a hot R process. You have something that has this extended n gamma gamma n equilibrium for a good portion of your calculation, as you saw it was holding for a while. Now let's look at a cold R process and just quickly remind yourself of what each of these is. Pink is neutron capture, yellow photodissociation, blue beta decay. And let's go ahead, and the boxed ones are n gamma gamma n equilibrium. Let's watch the cold R process proceed. Okay, here we go. We started out in n gamma gamma in equilibrium, but we're failing already very, very early. And it's beta decay and neutron capture that are competing. Photodissociation, although it was there for a bit, really does not show up very much. And your abundances are dominantly shaped between this competition of neutron capture and beta decay. Okay, so hopefully that gave you an intuition for how reactions are defined, how we apply these definitions, equilibrium, and some form of intuition for how to understand what's happening within your calculations, as well as a feeling for some of these R process slangs that you see in the literature: path, freeze out, cold, hot, things like this. Okay, so again, I think here we're going to take a bit of a break, because now we're going to come back and we're going to put all of this together and look at some recent works, some relatively recent works, which highlight the fundamental role of nuclear physics. You saw all of these different nuclear channels that are going to be contributing, that we have to account for. So what role do they play when you're trying to actually interpret your R process calculations compared to observation? We'll take a look at all that when we get back. So I'll see you in a bit.